start the recording. So we are already past task 3 with transverse expansion. So transverse expansion, this is the delta D. So when you were measuring the diameter at fracture, the diameter the sample should gain the diameter, not lose it. So this particular value cannot be negative. In some reports, it was negative. I don't know the reason. Maybe the instructions were not fully understood. But in a way, the net, or the delta D, or the difference between height, between the original height and the height at fracture. So there will be a value, but that value cannot be reciprocated as a gain. It will be lost in height. Then failure mode classifications. So all your materials, majority of them, apart from maybe a rubber, were displaying brittle fractures. There were different brittle fractures. So some were brittle, like extreme brittle fractures with grainy appearance, with river patterns or chevron patterns. Some fractures, for example, for the the white wax paraffin, depending on the rate of the loading, you could be lucky and you may get a cup and cone type of a fracture. Cup and cone is generally moderately ductile. So if you would be loading your sample gently and slowly, paraffin would collapse and create a cup and cone fracture. So that would be moderately ductile. However, on close examination, you would still see that the grains would be visible. So the material is granular, the material is crystalline, and the fracture itself, like if you would be holding the sample, it will fall apart. So it would be a brittle material fracturing in a semi or moderately ductile fashion. Okay, with key mechanical properties, you need to calculate the stresses and strains, the compressive strength, and also the corrected values. So there were really hardly any errors. So if calculations were correctly, if the measurements were correctly taken, there were no errors in calculations. When you were asked to plot stress versus strain, the answer was very simple. So you would plot stresses on the y-axis, you would plot strain on the x-axis. You only have 1 point of value for each individual material. If you had, rubber, if you had waxes, if you have ceramics, you would get the stress and you have a strain on the x-axis. That will give you a simple value on the x, on the stress-strain diagram. So you will have 3 dots. And these 3 dots needed to be connected from the origin, from the 0 point. And you would generally draw a line from the origin to the point. There will be just a straight line. There will be another straight line, and there will be another straight line. So if you connect these 3 lines, you will have like an aerial fan-like pattern. And that would be your stress-strain diagram that you would be required to draw. And that's it. So this is for the corrected value. Then when you had your 3 plastic samples, so the plastic samples that you had a translucent sample, which was polymethyl methacrylate. It was an acrylic, okay? The same acrylic that my spectacle lenses are made of, so PPMA. Then you had a so that acrylic was rigid. So same as spectacle lenses, they're rigid. And if you would heat it up, depending on the temperature, you may see the formation of bubbles inside that PPMA sample. And if you would increase the temperature as the sample is sort of standing upright, you will see that the sample will gently fold. If you overheat the sample, you may have dark regions, which is carbonization of PPMA, but you will see a bit of sort of bubbling and charcoaling on the sides, but the sample itself will still retain its structure and transparency to an extent. Again, we will not penalize students for visual records, because you had different temperature, you had different ways of looking at the samples. What was important is that the transparent rigid sample was a thermoplastic material. So the type of a polymer is thermoplastic, which means it can be remelted, it can be reformed. Some students, so the transparent sample, some students didn't really record the temperature at which it changed its properties. So PPMA overall would really react to a lower temperature, something around 100 to 130 degrees. You may report 140, 150, it's okay. Okay, so it depends where you would hold a nozzle next to that transparent rigid sample. But that was a PPMA, and that was a thermoplastic material. Another sample that you had was a semi-rigid, like a fairly flexible, but it's still rigid enough, translucent blue sample. It was a blue strip. That sample was polypropylene. Okay, polypropylene, it was a rigid polymer, semi-rigid polymer, and basically the blue color was the dye in a transparent polymer matrix. So polypropylene, like if we would look at the table that you had, it was the second listed from the top. It should have ideally had a higher melting temperature. It should be close to 160, 170, 180. Again, it's hard to be precise about the temperature measurements, but polypropylene, again, was thermoplastic. It could be reformed. Polypropylene itself, when you would place it in the vise and heat it, it will collapse, like it would simply fold on itself. And what you would see is that when you look at the zone where the heat was applied, that zone would become a little bit more transparent, and that would also become transparent, losing the blue color. Blue color are blue dyes, color dyes, that were mixed into the polymer. And as you would project heat onto that particular polymer, you would see that the heat basically was directed to polymeric chains. So in between polymeric chains, you would have dye molecules. Okay, so they were like interlocked. And as the heat was applied, the chains were shaking, and the dye would simply leach out of polymer chains and will be pushed into the periphery of the heat zone. So some students observed discoloration or increase of transparency in blue polypropylene polymer, glassification, often like because the texture of the polymer was a little bit rough, but you could make it a little bit smoother, or you could make it a little bit rougher. It's not really like an experimental research type of a point. It was more an experience. What was important, classify whether it's thermoplast or thermoset, it's thermoplast, and then relatively, not precisely, but in extent, differentiate the melting temperature between the polymers. So polypropylene should have had a higher temperature compared to acrylic by about 50 or 60 degrees. And if you could pick it up, that's great. Some groups picked it up really well. Okay, the tube that you had, I think it was a black tube. That was a silicon, okay? And silicon, no matter what you do to it, okay, even if you ran the hot gun above 300 degrees, as was not advised, but some students still did it, silicon did not react to the temperature. Silicon remained flexible. It was not reacting at the surface level. Like, to some degree, if you would really have a prolonged exposure, the surface will become a little bit dull and a little bit more opaque, but only at the surface level. Silicon was most non-reactive material. And some students confused it with rubber, which was okay. But you see in the table, the rubber was listed as disintegrating at about 150 degrees. So that wasn't a good candidate for a mystery answer. So, and silicon, it could not be reformed at the temperature, so it stayed in its shape. And if you would read the characteristics of the polymers, that was a clear giveaway. It was really only one material alongside with the melamine, and melamine is a tabletop material. So melamine is really rigid, and some of the descriptions it's been given. So yeah, identifying silicon was ideal if we could do it, but it was a thermoset material. Okay, answering individual questions, so I'll read them out. And in using question 1, using your results from tables 3-5, evaluate whether the measured corrected ultimate unconstrained compressive strength values provide a reliable basis for comparing the samples. Consider the influence of sample geometry, fracture mode, diametral expansion, and the assumption of a retained circular cross-section at fracture. State which source of uncertainty is likely to have the greatest effect on the calculated values, and explain why. Okay, so you see, like it's more of a scientific terming or scientific narration of the question. What basically question asks, like in the pedestrian way, and I could have wrote it, but I didn't. If you have your samples, like you have 3 different samples, right? So you have brittle ceramics, you have rubber, you have really, really soft ceramics. When you run a compression test and you got some data, so you got force data, you have the loss of height data, right? And you got the diametric expansion data. So you measured something, but you only ran one experiment. So do you think really that the values for compressive strength that you got are reliable values? Like, are they good enough values for you to use or not? So what do you think? Like, you can type maybe an answer, but I can provide my my answer to this question. So any ideas? Like, what would you think? Because we haven't seen a lot of really good answers in the reports so far. So some answered yes, it's a reliable, wonderful, leading to fracture, great. What do you think? Need a larger sample size? Yeah, well, the way, like in the research, for example, you see when we covered mathematical, like you remember we had just a couple of slides, I think it was in lecture maybe 4 or 5, when we looked at statistical variations, like a mean and average, right? And the deviation from the mean. So generally in engineering and science, we need to have at least 5 samples for reliable measurements, okay? So you get some statistical signal based on the performance of a material. Okay, so let us see, yeah, Jesse, you just answered, you need a larger sample size. I mean, larger, how big? Like a beer keg? Like a wheel tire from the car, or larger, just incrementally larger, right? Maybe, yeah, I will agree. So in a way, I would answer it the following way. Okay, again, we need to identify a source of uncertainty that will have the greatest effect on the values. So think about this. You had your samples. They came in different size and shape, right? They were not polished, cataloged, templated samples. The shape of the top and the bottom surfaces was rough, right? So the sample initially, so when you place a sample on the lower, on the low platelet, like on the anvil, the sample itself may not be aligned between the platelets, which means that if you are to run the compression test and your sample is at the slating angle or slightly asymmetric, right, you will immediately fracture it even with the lowest force, simply due to its misalignment. Okay, so the geometry of the sample and having a non-ideal sample with non-parallel bottom and top surfaces would be the most significant contribution to the error. Secondly, it was not a reliable technique to measure the diametric expansion just visually, right? So we did not examine where the crack was. It was arbitrary way of taking the measurements. If we would take the samples that we had seriously, we would need to have 5 to 10 more samples, but that really wasn't an option. So the most likely, the most significant source of error, a non-ideal sample. That's number one, like a sample geometry, sample shape. Then what you would have found is that when you fractured your sample, some samples had voids. Some samples that would have voids, cracks, inhomogeneities inside the sample. So the samples were not homogeneous. They were anisotropic, even S-cast, right? So sample anisotropy or non-ideal nature of the sample also contributed to the failure that you have observed. Then the rate at which the experiment was performed, it was not a gradual descent of the top platelet. So it was sometimes in a jerky motion, sometimes it was gradual, but it was not a controlled way, and the sample could not simply react by accumulating enough strain to react to the applied load. So it was a dynamic loading rather than a measured, more or less static loading. So if you would reflect on these factors, such as non-ideal geometry of the sample, non-isotropic or anisotropic nature of the material, the testing conditions that were somewhat ad hoc. Ad hoc means as given, like uncertified, non-standard, as like almost archaic, like garage type, right? So they were not in the measured, controlled manner. So these factors, such as sample geometry, sample material differentiation, and loading conditions and measurement conditions, so there were 4, contributed to the error in estimation of the strength. If I would point out to one most important, I would point out to the sample being placed non-ideal geometry of the sample. Okay, but again, if you would list 3 or 4 parameters or 3 or 4 factors, that will be good enough to get a full mark. Okay, let's go to question 2. So using your observations from table 6, and this is the plastic degradation of samples at increased temperatures. Explain how the thermal response of the polymer sample can be used to distinguish thermoplastics from thermosets. Relate the observed behavior during heating and cooling to molecular structure, including chain mobility, secondary bonding, and cross-linking. Justify your proposed polymer identification. So generally, this question asks you to regurgitate your observations and reflect on molecular chain structure of the polymers that you've tested. Okay, to reiterate, you had 3 samples. 2 of them were thermoplastics, the transparent acrylic and the blue strip, and 1 was thermoset, which was a silicon tubing. Okay, when we look at the bonding structure, thermoplastic polymers, they have long chains, and these long chains have covalent backbone, and the chains are joined together using very weak forces, such as van der Waals forces. The chains are free to move, slide, and they can sort of move relative to each other depending whether we stretch them, or if we heat them up, they can shake themselves out from the space or from the volume. So this is what thermoplastic materials do. Thermoset materials, such as a silicon, it still has backbones. So the backbone in silicon, we really didn't cover it, but maybe now it's a good time. So the silicon itself, rather than having carbon to carbon backbone, it has silicon backbones. Okay, the backbone itself, it's still covalent. So silicon to silicon are joined together really strongly. And then there are auxiliary grafted branches that grow from the backbone outwards, okay, like a branch on the tree. And each of the branches is connected to another backbone. So essentially, in thermoset polymers, the structure is fused together. So the backbones are fused together permanently. It's almost like you have a strand of backbones which are strong, running alongside each other, and then they're fused together with little branches. And these branches are also strong, okay? Which means the overall structure is very rigid. And in thermosets, the structure is fused together during the chemical or thermal polymerization, which means that it requires the same amount of energy to rupture the backbone, same as to separate the backbones of a polymer in the same manner. Okay, so it's almost like a 3-dimensionally linked. So thermosets are cross-linked polymers, and they will thermally degrade simply for the reason that as you provide energy to them, they will not remelt, they will not reform, they cannot be reshaped or recycled, simply that any heat will be used to break the bonds in the backbone or in the strong covalent connections between the backbones. So we've discussed, mobility in thermoplastics is very high because chains can slide relative to each other. Secondary bonding is weak in thermoplastics, and cross-linking is absent in thermoplastics, but it's present in thermosets. So that's basically the answer to this particular question. So if you would differentiate between thermoplasts and thermosets based on the structural backbone connections, that will be sufficient enough. Okay, question 3 is really tricky, and I have eavesdropped into some groups as they were discussing question 3. Okay, a component is required to operate under moderate compressive load, occasional surface abrasion, and short-term heating. Based on the results from scratch hardness, compression testing, failure mode classification, and thermal response, determine whether a ceramic, polymer, or a ceramic polymer hybrid would be the most suitable choice? Justify your answer by discussing the main property trade-off and likely failure risks. Okay, any ideas? Because it was a bit of a ratty question. I'm sorry for putting it this way. Any ideas? Anyone remembers what they wrote? Yes, ceramics hybrids. Yes, that's very good. Okay, so what this question implied is basically flooring. Okay, floors, like on the floor we have planks. So a lot of students, when they read this question, they said, oh, it's all rubbish, it's impossible. Okay, we can't mix ceramics and polymers together. That's all nonsense, right? And they said it's, you know, ceramics are too brittle and ceramics are too fragile, and they could be either be strong or they could be weak, but nonetheless, they're brittle. And then polymers, they're flexible and they really don't mix with ceramics because they have a different chemical structure, which was correct when you assess materials by themselves in isolated environment. However, you can still fuse them together. So, I mean, you can have a, you know, a what do you call it, cement covered in polyurethane resin, sort of to prevent it from degradation, or vice versa. You can have a hybrid flooring where you have either ceramic at the top and polymer at the bottom, or you can have polymer at the top and ceramic at the bottom. So essentially, if you have, like, for example, in hybrid flooring, so what you have high wearing polymer at the top, which is wear resistant, and it can withstand moderate heating, it can withstand moderate physical loads, while the base, which is a composite ceramic, provides a padding. Okay, you can also inverse it and engineer a ceramic type of a coating on the flexible or semi-flexible base. Okay, so it's possible. Again, if you strongly justify that's not impossible and you reflect on the properties, great, you know, you'll get a mark. If you think about it, it's possible, and you state the properties, that's also great, you will get a mark. Okay, right, finally, multiple choice questions. So I'll read them out. So multiple choice, the question: during the unconfined compression test, a ceramic sample fractures at a relatively small axial strain and shows a little measurable diametral expansion before fracture. Which interpretation is most consistent with this behavior? So what it means is that as we compress the sample, like we load the sample little and it's already done, it's already fractured. And it didn't even show that it swelled up. It didn't gain any diameter at all. So what does it mean? Option A, the material likely underwent significant plastic flow before fracture, causing energy absorption and recovery. No, it didn't do anything plastic, right? Option B, the material likely failed by brittle crack propagation with limited capacity for lateral deformation and little tolerance to local stress concentrations. Yes, okay, this is the correct answer. So, I mean, it failed brittle crack propagation, limited capacity, so limited because it failed at very little loading. So lateral means this, okay, diametral means that. So with limited capacity for lateral deformation, so it didn't deform height-wise, and little tolerance to local stress concentration. So as soon as we loaded it, it's not tolerating any stresses and it just decided to give up. Okay, so that option B is correct. Option C, the material exhibited high toughness, already incorrect answer, because minimal diametral strain indicates strong resistance to crack initiation. No, it contradicts the question. Option D, the material interatomic bonding strength increased during loading, causing axial strain to increase without significant stress built up. That's nonsense. Okay. So that's the answer is B. Okay, another question. A polymer sample softens gradually on heating. It can be bent while hot and retains a permanently deformed shape after cooling. Which explanation best accounts for this behavior? Okay, so what question implies is that if we heat a polymer, it softens and then becomes stiff and retains its shape. We can heat it again, it softens and retains its shape. We can heat it again, softens, heats its shape. So it actually, the question asks about a thermoplastic polymer already. So option A, the polymer contains highly cross-linked network that prevents chain motion until thermal decomposition begins. No, that's wrong. This is wrong, okay? So no, it's not cross-linked and it does not decompose. Option B, heating weakens secondary interactions between the chains, correct, for allowing molecular segments to move relative to one another without breaking the primary covalent backbone. Yes, this is a correct answer. Option C, material behaves this way because ionic bonds between chains become stronger at elevated temperature. Nonsense. Option D, the polymer must be thermoset since permanent deformation after cooling indicates irreversible bond scission. Again, nonsense, just a contraption of different words. Okay, last multiple choice question. A material shows a relatively high scratch hardness but low corrected compressive strength and fails by sudden fracture with a little strain. Which statement best explains this combination of properties? Okay, let's uncouple that question. Material shows a relatively high scratch hardness but a low corrected strength. So this is like concrete or cement. So it's relatively high scratch hardness, but when we load it, it just cracks. So on the surface it's hard, but as we load it, like as a bulk, like as a barrel or a block or a piece of brick, it just suddenly shatters. Which statement best explains this combination of properties? Okay. Option A, high resistance to surface indentation or scratching does not necessarily imply high resistance to bulk fracture under compressive strength. Yes, this is correct. This is just a general observation. That's true. I mean, it's just stating the fact. Yes, it could be hard, but it does not really immediately imply that the hard material should not fail, right? So this is just a logical verbalization of the physical observation. Option B, the material must contain metallic bonding, already wrong, okay, which increases hardness but reduces compressive strength. That's nonsense. Then the material, option C, likely became ductile during testing. No, it did not, causing its compressive strength to decrease below its hardness. It's just a combination of words I've written for fun. Okay, wrong. Option D, scratch hardness and compressive strength always measure the same deformation mechanism. Okay, when you have words like always, it's always wrong. Okay, there aren't really any phenomena that always acts in always the same always manner. Okay, when you have a word always, ignore it. It's wrong. Okay, so anyway, I'll read out the question fully. So scratch hardness and compressive strength always measure the same deformation mechanism, so the result is inherently inconsistent. No. And that's it. Right, so there are 11 of you staying on out of 385 in the class. So at 6 o'clock on Monday. Any questions, guys? All good. There will be slightly higher marks, I think, compared to lab 2 in lab 3 once we mark it. Okay, let me close the recording.